Welcome to section 4.2, Polynomial Functions and Models. Graphs of polynomial functions. A turning point occurs whenever the graph of a polynomial function changes from increasing to decreasing or decreasing to increasing. Let's look at this example we have below. As I move from left to right, I see my graph decreasing up until the point -2, -3. Then I see my graph increasing up until the point 1, 3, and then it appears my graph is decreasing again as my x's go towards infinity. So I see that I have two turning points. I have the point -2, -3, as well as the point 1, 3. So my turning points where my graph changes from increasing to decreasing or decreasing to increasing happen at -2, -3, and 1, 3. Another thing we can talk about from this graph is the end behavior. End behavior is a description of what happens to a graph as either x becomes very large, that is, x is approaching infinity, or x becomes very small, that is, x approaches negative infinity. Let's look at our graph again. On our graph, I can see that my f of x values here are going up towards positive infinity as my x values are getting small. So as I move my way to the left on the number line, my graph is going up towards infinity. So f of x approaches infinity as my x values get very small, or as my x values go towards negative infinity. And notice my f of x values or my y values are going down towards negative infinity as my x values are getting very large. So if this graph were to keep going down forever, it would keep also kind of going outward. As my x's are getting really, really big, my y's are getting very, very small. Consider the following types of functions and discuss their graphs. Number 1, we have a constant function. If f of x equals a, where a is non-zero, then f is both a constant function and a polynomial function of degree 0. The constant function f of x equals a could be, for example, f of x equals 3. So that would give us back this graph. Or what we see is that the graph is a horizontal line and for this type of horizontal line where a is not equal to 0, we are going to have 0 x-intercepts and 0 turning points. If a is equal to 0, then we consider f to have an undefined degree. And remember, that would be the line that's actually the x-axis. So if we're not considering the line where a is equal to 0, we're never going to touch the x-axis, so we're never going to have any x-intercepts, and we're never going to change from increasing to decreasing, so we never have any turning points. The second function we have is a linear function. If f of x equals ax plus b, we used to write mx plus b, but now we're using a, where a is non-zero, then f is both a linear function and a polynomial function of degree 1. So maybe we have a line like this one. Or we could also have a line with a negative slope. Either way, the graph is a line that is not vertical or horizontal. The graph will have 1 x-intercept and 0 turning points. If we're talking about a line, and the line never changes from increasing to decreasing or decreasing to increasing. It is always increasing or always decreasing. So I'm never going to have a turning point. Now, the end behavior for our red graph tends to negative infinity on the left and positive infinity on the right. And this happens when you have a positive slope. Well, for us, we're thinking of our slope as a. So this happens when a is greater than 0. Again, we have ax plus b. Think of it like mx plus b. If m was positive, we would get back a line like the red line. For our green graph, the end behavior tends towards positive infinity on the left and negative infinity on the right. And this happens when we have a negative slope. Saying positive infinity on the left means our y values are getting larger as our x values are getting smaller. And negative infinity on the right means that our y values are going down and getting smaller as our x values are getting larger. The quadratic function. If f of x equals ax squared plus bx plus c, where a is non-zero, then f is both a quadratic function and a polynomial function of degree 2. We talked about quadratic functions in the last chapter, and we saw a few different cases about how it may interact with the x-axis. For starters, we have the case where our parabola never touches the x-axis. Then we also have the case where our parabola just touches the x-axis once. And the last type of parabola we have is when our parabola crosses the x-axis twice. Again, like I've been saying, the graph is a parabola. And we can either have 0, 1, or 2 x-intercepts. But regardless of the x-intercepts, we have exactly one turning point. If you look at any of our graphs, they transition either from decreasing to increasing or increasing to decreasing only one time. That point where we have our turning point for our parabolas is what we've been calling our vertex. The end behavior tends to positive infinity on both sides, like in graph 1 and graph 3, when a is positive. Remember, if our leading coefficient is positive, our graph opens upward. And the end behavior tends towards negative infinity, like in our second graph, on both sides when we open downward or when a is less than 0. The cubic function. If f of x equals ax cubed plus bx squared plus cx plus d, and a is not equal to 0, then f is both a cubic function and a polynomial function of degree 3. Hopefully you're noticing by now that the highest power you have, or the largest exponent, is going to tell you the degree of your polynomial. So cubics are degree 3, quadratics were degree 2. Okay, some examples of a cubic function. Maybe we have something like this, or this, or even this. But in the first graph, notice that I have 1, 2, 3 x-intercepts. In the second one, I only have 1. And in the third one I drew, I have 2. So our graphs can have 1, 2, or 3 x-intercepts with either 0 or 2 turning points. For my first graph, I have a turning point here and here. For my last graph, I also have a turning point both here and here. But in my middle graph, this graph is increasing all the time. So I never go down to decreasing, so I have 0 turning points. The end behavior tends to negative infinity on the left and positive infinity on the right when our a value is positive. And our end behavior will tend to positive infinity on the left and negative infinity on the right if our a value is negative. No matter what, when dealing with the cubic function, your graph must cross the x-axis at least once. Since our end behavior is always pointing in opposite directions, either negative positive or positive negative, at some point we'll have to cross through the x-axis. A quartic function. If f of x equals ax to the fourth plus bx to the third plus cx squared plus dx plus e, and a is not equal to 0, then f is both a quartic function and a polynomial function of degree 4. Here are some examples of quartic functions. All right, in the first picture I drew, I have 1, 2, 3, 4 x-intercepts. In the second one, I only have 2. In the third one, I have 3. And in fact, your graph can have up to 4 x-intercepts. So we could have anything less than 4, but up to 4. And up to 3 turning points. Notice in my first graph, I have 1, 2, 3 turning points. In my second graph, I only have 1 turning point. Notice I'm increasing this whole time, and then I change to decreasing. And in my third graph, I have 1, 2, 3 turning points. The end behavior tends to positive infinity on both sides when a is positive, and negative infinity on both sides if a is negative. Degree, x-intercepts, and turning points. The graph of a polynomial function of degree n with n greater than or equal to 0 has at most n x-intercepts and at most n minus 1 turning points. So let's go check that. When I had a quartic, which is degree 4, I had at most 4 x-intercepts and 4 minus 1, which is 3 turning points. When I was cubic, which is degree 3, I could have up to 3 x-intercepts and 3 minus 1, or 2 turning points. When I was degree 2, n is 2, I could have up to 2 x-intercepts, and 2 minus 1 is 1, which is 1 turning point. And when I was linear, which is 1, I could have 1 x-intercept and 1 minus 1, which is 0 turning points. Okay, using all of the information we just went over and all of the information in the types of polynomials chart that we filled out, try problem 1 on your own. Pause the video, come back, check your answer. It might be helpful if you wrote the function in descending order, which means from largest to smallest in regards to power. Then it's pretty obvious that the largest power we have is 4. So the degree of this polynomial is 4. The leading coefficient is the coefficient multiplied by your x to power 4 here, since that was our degree. So our leading coefficient, which we call a, is negative 1/2. The end behavior, well, if I'm degree 4, I'm a quartic function, and my a is negative. So I'm quartic with a negative. Going back to our chart, we see that for quartic functions, if a is negative, then the end behavior tends to negative infinity on both sides. And an even nicer way to write this is f of x goes to negative infinity as x goes towards negative infinity. So for small x values, I'm going towards negative infinity. And again, my graph still approaches negative infinity even as my x values get very large. Okay, it says to check your answer with the graph, so I'm going to utilize a website called Desmos. And I'm going to type in the function that we were talking about. So we have 3 minus 5x plus 2x to the third minus 1/2 x to the fourth. And looking at this graph, I do see that my end behavior goes towards negative infinity as my x's are getting smaller. We could even zoom out and see as we go farther and farther to the left, our graph is still going down towards negative infinity. And as my x values get larger, my graph is still going down towards negative infinity. Concavity. Polynomial functions of degree 2 or greater, so quadratic functions or higher, have graphs that are curves. Concavity is a mathematical description of how a curve bends. So let's just look at parabolas. When I have a parabola pointing upward, this is called concave up. And when I have a parabola that points downward, this is concave down. That's my cat. Okay, if a curve switches between concave up and concave down, the exact point where the concavity switches is called the point of inflection. For example, let's say we have this graph. We can see for this portion of the graph, it looks as if our graph is concave up. But then there's kind of a turning point, or I guess I shouldn't use that word, but a point of inflection, where all of a sudden I could say that the graph is concave down. This point in the middle here, wherever that might be for your graph, is what we call our point of inflection. So in the one I drew, it's at 0, 0. Piecewise polynomial functions. For exercise 2, what I want to do is I want to sketch a graph of this function f of x equals 0.5 x squared when x is between -4 and -2, including x when x is between -2 and 2, not including, and x squared minus 4 when x is between 2 and 4 including. We've seen piecewise functions before, we did them in class, and it's basically just a function made up of pieces of functions depending on certain parts of its domain, or I should say defined for certain parts of its domain. So let's graph f and then determine if this graph is continuous, as well as solve f of x equals 0. Okay, the top of our function, I'm going to do in orange, is 0.5 x squared. Well, the smallest value I'm allowed to plug in for x is negative 4. So let's start by plugging in negative 4. Well, negative 4 squared is 16, so I have 0.5 times 16, which is 8. Negative 4 is included because of that equal sign, so I'm going to plot the point negative 4, 8. So 1, 2, 3, 4, 2, 3, 4, 5, 6, 7, 8. So right here. Now I'm going to plug in negative 3, I think, and negative 2. When I plug in negative 3, I get 4.5. And when I plug in negative 2, I get 2. Now looking at this function, I have x squared, so I know this is a parabola, so I expect this to be kind of a curved shape. I filled in the dots at negative 4 and negative 2 because both of those are included for my x values. Now let's graph x for between negative 2 and 2. Well, this is just a line with slope 1 passing through the origin. So when I plug in negative 2, I just get negative 2. But this negative 2 is not included, so I'm going to have an open circle. If I plug in negative 1, again, I just get negative 1. 0 gives me 0. 1 gives me 1. But when I plug in 2, which is not included, I get back 2, but I need an open circle. And this is a line. And the last part of our graph, I'll do in green. The smallest value I can plug in is 2, so I have 2 squared minus 4, which is 0. So when I plug in 2, I get 0, and it's included, so I fill it in. I'll plug in 3, which gives me 5. And I'll plug in 4, which is also included. This gives me 16 minus 4, which is 12. So this is 5, 6, 7, 8, 9, 10, 11. We'll have to go up one more, then that's actually there. And again, this is x squared minus 4, so this is a parabola, so I expect kind of a curved shape. Okay, this is the graph of our piecewise function. We were asked if this graph is continuous. So if you remember from our lecture in class, your graph is continuous if you can draw the entire thing without ever picking up your pen. Well, I have quite a few jumps where I have to pick up my pen. I have this gap here as well as this gap here. So because of those gaps, f is not continuous. And I was also asked to identify where f of x equals 0. Well, if f of x equals 0, remember f of x is like your y value. So this is just asking for our x-intercepts, which are at x equals 0 and x equals 2.